Hello everybody. In this lesson we're going to learn how to use an equation called Henderson-Hasselbalch. Sometimes you'll see people abbreviate it HEHA because nobody wants to have to write out that entire thing every time. So we're going to use this equation when we have something called a buffered solution. A buffer is something that you make that will resist a change in pH when you add either an acid or a base to it. So it's going to stop the pH from changing as rapidly as it would if the buffer was not there. So to make a buffer, you use a weak acid and a salt that goes with it, or you make a weak base with its salt there. So one or the other, depending on what you're doing. So you can see here, I've put some acids, weak acid here, and then showing you what the salt of that weak acid would be. So I tried to kind of highlight in red the part that came from the acid, and then the cation is coming from that strong base, which you can see here in blue. It is incredibly important that you're very, very familiar with your acids and bases, strong ones, weak ones, so that you will recognize your salts when you see them. And so that you will know which salts you could use if you want to make a buffer. One of the things that is hard in this chapter is that I don't really have tricks to help you memorize your strong acids, bases, salts, recognize them. It comes with repeated exposure. You can find a variety of mnemonics that might help you online, but you really need to get to the point where it's so familiar to you that when you look at this one right here, you know, oh, yeah, that came from formic acid. Or potassium fluoride, that came from my hydrofluoric acid. It needs to be a quick thing that you notice. Here are some examples of using the weak base and then the salts that would go with it. I think these tend to be harder to recognize. Our brains have a harder time remembering these bases, so give them a little extra attention when you get those practice problems so that you're going to recognize things when you see them. And I'm not a huge proponent of flashcards in chemistry. I don't think that they help as efficiently as other types of study techniques, but I've noticed with buffers and salts, sometimes making some flashcards of combos of acids and salts and bases and salts that would work can be helpful for that quick recognition. So let's walk through one of these. Okay, it says to calculate the concentration of our hydrogen in a solution that's 0.1 molar in sodium fluoride and 0.2 molar in our hydrofluoric acid, and it gives us the Ka for the acid. So you should notice here that we have an acid and we have the salt. And one of the things that a lot of students forget is that hydrofluoric acid is considered a weak acid. It's not strong. And so that kind of throws people off because things like hydrochloric is strong, but hydrofluoric is not. So this is a weak acid and a salt combo that came from it. So I'm going to have my dissociation here. And if you were to try to write your law of mass action, we would get that. And the big deal here, the thing that makes this problem a little bit different than the things we've been doing so far, is that you are already going to have some of your fluoride present when you start because your sodium fluoride is in this mixture. And so that's going to affect our calculations, isn't it? So why don't you try to plug in the values and get a value for your hydrogen concentration. All right, so I've plugged everything in, and I find that my concentration is 1.44 times 10 to the minus 3. If you were to redo this problem and it wasn't a salt present, you would get a different concentration, wouldn't you? So now we can calculate the pH just like we normally would, like that. When we look at graphs of a titration for something that does not have a buffer and something that does have a buffer, we are going to notice something a little bit different about the shape of the curve. So here we have our acetic acid and we are titrating it with sodium hydroxide. And there's no buffer present. There's no salt here to go with our weak acid. So take a second, kind of look at the shape of that curve because I'm going to want you to compare it to something in a minute. So pause and kind of look at that shape. Okay, now look at this. Now we have our weak acid mixed with a salt, and then I'm going to titrate it with my base. You should notice something about that curve. It's the same concentration of acid, it's the same concentration of base, but we see a little bit of a change here. Do you notice that in the unbuffered one, it changed its pH a little bit more rapidly? Whereas when it's buffered, you can see it here if I overlay these. It has a little bit flatter of a section here, doesn't it? That is a big deal. In biology, they use a lot of buffers because a lot of biological processes are only going to work in a certain pH range. And so by having a buffer present, you can really keep the little scenario you have, whatever the situation is or reaction or process they're dealing with, you can keep it in the good pH range because the buffer will help mitigate any changes that are occurring. So you might have learned about that in bio. Now, there is an equation called the Henderson-Hasselbalch equation. Now, you don't technically need to use this. You could do a series of ice tables and things like that. That tends to be a bit time consuming for students. AP would like you to use the Henderson-Hasselbalch equation. On my answer keys, I've tried to have a little bit of a variety so that you can see it doesn't really matter as long as you get the right answer. So this is a great shortcut. There's going to be two versions of this equation. One is for calculating the pH, where you're going to have the pKa plus log of the anion over the acid. So it's the base that you have present over the acid. To find pOH, it's backwards, isn't it? And you're going to use pKb, so be careful about that. So if you're looking for pH, the acid goes on the bottom. If you're looking for pOH, the base goes on the bottom. That's how I remember it. And you may be wondering, what is this pKa and this pKb? It's nothing special. Just like we would do pH, negative log, that's what you're doing. It's the negative log of the Ka or the negative log of the Kb instead of the negative log of your hydrogen, right? So it's not anything fancy. What trips students up is that your acid or base is probably going to be that conjugate from the salt. And so if you don't recognize your salts and you don't know which things are acids and which things are bases, you don't know which number to put where. You don't know what's going to go on your numerator. You're not going to know what goes on the denominator. You're not going to know to use a pKa versus a pKb. So that's where it gets a bit tricky. So that's just the little way that I remember, right? Now, one thing that I like to do is show you a slightly different version of these. It's not anything different. It's just a different way to think about it because we're primarily using these salts. Your salt is the conjugate base to the acid, isn't it? So why not just write that? And here, your salt is the conjugate acid of your base. Now, if you are really struggling with your conjugates, it may be a good idea to bust out 2 different color highlighters and color code things like you see I've done here. Clearly, you're not going to do that in the middle of the AP test, right? But color coding it might help your brain latch on to the idea of conjugates to help you recognize them. Another small tidbit that can make these concentrations difficult to get is that you have to remember to check your formulas. You remember we learned about the Van 't Hoff factor where we have to think about how many particles things are dissociating into? We have to do that here as well. If you dump in magnesium chloride or whatever, something like this, you get 2 chlorines, don't you, for each one of these molecules. So if you have 1 molar magnesium chloride, you really have 2 molar chloride. So you have to be real careful about that when it comes time to plug things into these concentrations. So let's try this again. You'll notice these are the same numbers, aren't they? The same problem, but let's try using that little trick formula that we have. So as we saw before, we have our weak acid mixed with the salt. That salt has the conjugate base from our acid, that fluoride ion. So I can use this equation and plug my numbers in to go to pH directly. Now, if you notice, this question actually didn't ask us to go directly to pH, did it? A lot of them do. Very common to want to know the pH. But it doesn't matter. You could still use this even though we're looking for the concentration of our hydrogen. So I'm going to plug in the negative log of my Ka value plus log of the fluoride ion, the base, the conjugate base, the salt, and it's a 1-to-1, right? There's only 1 fluoride for each sodium fluoride, so that's a 1-to-1. And then I have my acid concentration on the bottom to get my pH. And if you remember your basic pH calculations, if you have the pH but you want the concentration of hydrogen, you can just do 10 to the negative pH. And we get the exact same answer as before. People are going to have a personal preference and a habit for using different equations. And that's okay. Totally fine. If you look at this and think, I really like the other one better, that's fine as long as you can do your preference quickly and the way you like to do it works with all versions of the problems. Not all versions can use each method. Here's a couple other rearrangements that I personally really like. I like using my law of mass action to be able to just rearrange it. And I like thinking about it as the acid and the salt, or down here, the base and the salt. If I were you, I would spend some amount of time and effort getting used to the generic versions of some of these equations. You see how we use HA and BH, things like that, because that can also help you recognize the different salts and acids and bases. So these are all great rearrangements to get to the same goal. So some of the pros and cons, I really like presenting you with these and then letting you pick and choose, right? So for the ice tables, they are familiar. We're comfortable with doing them at this point. I really, really hope. The con is that can take a long time. I see people lose time and not finish. The He-Ha equation, that Henderson-Hasselbalch, is really fast, and if you look at the equation sheet, it's on the back. And so that's something that is nice, a little bit of a comfort blanket, right? You know it's there on the back of the equation if you freeze and you forget. But I've noticed that sometimes people struggle because if it's not flat out asking you to solve for pH, they forget that they can use it and they waste a lot of time wondering what they should do. So you saw in the problem we did together, I used the Henderson-Hasselbalch to get pH and then I did something with that to convert it. But sometimes people freeze and forget those extra steps at the end. And then the other way I like to do it is just rearranging that law of mass action. I find that to be very simple. I find it to be very straightforward. The con is that you have to recognize it. And then if you are trying to get pH or POH, then it's one more step. Whereas if you're trying to solve for pH, Henderson-Hasselbalch already gets it to you in one step. So, kind of a pick your poison, right? You decide what works best for which practice problems. But I will really, really suggest and really ask that you practice all of them a little bit. I think if you can practice all of the methods, it will give you a little bit of comfortability with the material. And if you are all anxious on a quiz or stressed out during the AP test and your brain freezes, then your brain has alternate pathways it can pursue to get to the end result, right? If you can't remember how to use Henderson-Hasselbalch, you can remind yourself, okay, just think of an ice table. I can do an ice table. So it allows your brain alternates to pursue when it gets nervous and stressed out. Okay? And remember, I don't want to get 5 bazillion text messages at 11:30 at night asking me if it matters whether or not I did it one way and you did it another. Nope, does not matter. You will get credit as long as it is a valid method and you've adequately shown your work for that method. When you look at an AP rubric and they divvy out partial credit, say it's 3-point problem, if you use a different method, you will still be eligible for 3 points. The partial credit may just be allotted differently. So that's something else to pay attention to, is look at some of those AP rubrics for where they're breaking the points down on these buffer problems, because that will help you see where the common mistakes are, and you can kind of focus your attention and make sure you're studying those real key places where you could get points. Okay? All right, everybody, that is it. I hope that was helpful. Bye.